Hello, universe. Today we're going to be showing that if r is a rational number and x is irrational, we must have that r plus x is irrational and r times x is irrational. Okay? So we're going to assume, for sake of contradiction, that r plus x is a rational number. This means that r plus x can be written as the ratio of two integers. R plus x is equal to, let's say, m over n for some m and n belonging to the integers. Since r is rational, then r can also be written in this form. So since r is rational by our assumption, then r is equal to, let's say, r1 over r2 for some integers r1, r2. Okay, but then this tells me that, in fact, x can be written as m over n minus r1 over r2. And then if we find the common denominator here, we'll multiply this fraction on the top and bottom by r2, multiply this fraction on the top and bottom by n, and I'm going to get m times r2 minus n times r1 is all divided by n times r2. Right there. Okay? All right. So now, we've shown that x is of the form, let's say, x1 over x2, where x1 is m times r2 minus n times r1. And x2 is just r2 times n. I'll write it as n times r2. But all of these m, r2, r1, and n are all integers by our construction, by our definitions here. And since the integers are closed under multiplication and addition, this is what makes them into what's called a ring, then in fact this number is an integer because it's simply a difference of two integers, and a difference and a product of two integers. Product of two integers is an integer. The difference of two integers is an integer. So x1 is an integer. Similarly, x2 is an integer. And this means that x must be a rational number by definition. And this is the contradiction. Okay? So that proves the first part of the claim. Let's move on to the next one. Okay, so we're still going to assume, for sake of contradiction, that r times x is a rational number. So I can say there exists m and n integers such that Rx is the ratio of these two integers, let's say m over n, okay? Also, again, since R is rational, we have that R is equal to R1 over R2 for some integers R1 and R2. So I should say there exists R1, R2 integers such that So I'm using a little bit of different notation for this part, just to kind of get you more familiar with this notation. This symbol just means there exists, and this symbol means belonging to. This ST means such that. So it's kind of a shorthand notation here. Okay, so now we have, plugging this in, we have R1 or R2 times X is equal to M over N. Okay, but now I can multiply this expression by the inverse of R1 over R2. So namely, I can multiply this expression on both sides by R2 over R1. Okay? And in doing so, I'm going to get, and this is, I probably shouldn't write it in this way. This is maybe more scratch work. If I really want to do a proof, then I need to separate this line here. So I need to say this equality holds as one line of my proof. And then the next line tells me that I can multiply both sides of the equations by R2 over R1. Okay, and then multiplication is going to be associative, so this is going to just be equal to R2 over R1 times R1 over R2. So this is just 1 times X is R2M over R1N. Okay? And so, yeah, X is equal to R2M R1N. And R2M, this is an integer, and R1N is an integer. So since these two numbers are integers, this is a 2 here. Since these two are integers, this tells me that X must be a rational number, which is a contradiction. So I conclude that my original hypothesis, Rx is a rational number, must be false. Therefore, Rx must be irrational. Okay.